Hi learners, welcome to our science class. In today's video, we will discuss Newton's second law of motion, which is also known as the law of acceleration. Here are the objectives of the lesson. By the end of this session, you will be able to define acceleration, understand Newton's second law of motion, explain the difference between weight and mass, and calculate the force, mass, and acceleration by solving a word problem about the law of acceleration. Let us have a short recall from the previous lesson. From the previous video, you have learned about the first law of motion, which is the law of inertia. I want you to complete the following statement. Choose your answer inside the box. You may type your answer in the comment section. You have 5 seconds to answer each. Number 1. Blank is the property of a massive object to resist changes in its state of motion. The correct answer is inertia. Number 2. Blank is a quantity that is dependent upon the inertia of an object. The correct answer is mass. Number 3. The more inertia that an object has, the blank mass that it has. The correct answer is more. Number 4. The first law of motion is also known as blank. The correct answer is the law of inertia. Number 5. The law of inertia states that an object at rest stays at rest and an object in motion stays in motion with the same speed and the same direction unless acted upon by a blank force. The correct answer is unbalanced. Well done, learners. Let us proceed to the lesson. Newton's second law of motion is closely related to Newton's first law of motion. It mathematically states the cause-and-effect relationship between force and changes in motion. Newton's second law of motion is more quantitative and is used extensively to calculate what happens in situations involving a force. Before we can write down Newton's second law as a simple equation giving the exact relationship of force, mass, and acceleration, we need to sharpen some ideas that have already been mentioned. First, what do we mean by a change in motion? The answer is that a change in motion is equivalent to a change in velocity. A change in velocity means, by definition, that there is an acceleration. Newton's first law says that a net external force causes a change in motion. Thus, we see that a net external force causes acceleration. Another question immediately arises. What do we mean by an external force? An intuitive notion of external is correct. An external force acts from outside the system of interest. For example, in Figure 1 the system of interest is the wagon plus the child in it. The two forces exerted by the other children are external forces. An internal force acts between elements of the system. Again, looking at Figure 1, the force the child in the wagon exerts to hang on to the wagon is an internal force between elements of the system of interest. Only external forces affect the motion of a system, according to Newton's first law. You must define the boundaries of the system before you can determine which forces are external. Sometimes the system is obvious, whereas other times identifying the boundaries of a system is more subtle. This figure shows different forces exerted on the same mass produce different accelerations. Letter A shows 2 children push a wagon with a child in it. Arrows representing all external forces are shown. The system of interest is the wagon and its rider. The weight W of the system and the support of the ground, N, are also shown for completeness and are assumed to cancel. The vector, F, represents the friction acting on the wagon, and it acts to the left, opposing the motion of the wagon. Letter B shows all the external forces acting on the system add together to produce a net force, F net. The free body diagram shows all the forces acting on the system of interest. The dot represents the center of mass of the system. Each force vector extends from this dot. Because 2 forces are acting to the right, we draw the vectors column early. Letter C shows A larger net external force produces a larger acceleration. The prime is greater than a, when an adult pushes the child. Now, it seems reasonable that acceleration should be directly proportional to and in the same direction as the net, total, external force acting on a system. This assumption has been verified experimentally and is illustrated in Figure 1. In a part letter A, a smaller force causes a smaller acceleration than the larger force illustrated in part letter C. For completeness, the vertical forces are also shown. They are assumed to cancel since there is no acceleration in the vertical direction. The vertical forces are the weight W and the support of the ground, N, and the horizontal force F represents the force of friction. These will be discussed in more detail in later sections. For now, we will define friction as a force that opposes the motion past each other of objects that are touching. Figure 1 letter B shows how vectors representing the external forces add together to produce a net force. To obtain an equation for Newton's second law, we first write the relationship of acceleration and net external force as the proportionality of a prop to F net, where the symbol prop to means proportional to, and F net is the net external force. This proportionality states what we have said in words: acceleration is directly proportional to the net external force. In this figure 2, the same force exerted on systems of different masses produces different accelerations. Letter shows, a basketball player pushes on a basketball to make a pass. The effect of gravity on the ball is ignored. Letter B shows, the same player exerts an identical force on a stalled SUV and produces a far smaller acceleration, even if friction is negligible. And the letter C shows the free body diagrams are identical, permitting direct comparison of the two situations. A series of patterns for the free body diagram will emerge as you do more problems. Now, it also seems reasonable that acceleration should be inversely proportional to the mass of the system. In other words, the larger the mass, the inertia, the smaller the acceleration produced by a given force. And indeed, as illustrated in Figure 2, the same net external force applied to a car produces a much smaller acceleration than when applied to a basketball. The proportionality is written as a prop to 1 over m, where m is the mass of the system. It has been found that the acceleration of an object depends only on the net external force and the mass of the object. Combining the two proportionalities just given yields Newton's second law of motion. The acceleration of a system is directly proportional to and in the same direction as the net external force acting on the system, and inversely proportional to its mass. In equation form, Newton's second law of motion is equal to F net over m. This is often written in the more familiar form F net equals ma. F net equals ma is used to define the units of force in terms of the three basic units for mass, length, and time. The SI unit of force is called the Newton, abbreviated N, and is the force needed to accelerate a 1 kg system at the rate of 1 meter per second squared. That is, since F net equals ma, 1 Newton equals 1 kg times meter per second squared. When an object is dropped, it accelerates toward the center of Earth. Newton's second law states that a net force on an object is responsible for its acceleration. If air resistance is negligible, the net force on a falling object is the gravitational force, commonly called its weight. W weight can be denoted as a vector W because it has a direction. Down is, by definition, the direction of gravity, and hence weight is a downward force. The magnitude of weight is denoted as W. Galileo was instrumental in showing that, in the absence of air resistance, all objects fall with the same acceleration, g. Using Galileo's result and Newton's second law, we can derive an equation for weight. Consider an object with mass, m, falling downward toward Earth. It experiences only the downward force of gravity, which has magnitude, w. Newton's second law states that the magnitude of the net external force on an object is F net equals ma. Since the object experiences only the downward force of gravity, F net equals w. We know that the acceleration of an object due to gravity is g, or a equals g. Substituting these into Newton's second law gives. This is the equation for weight. The gravitational force on a mass, m, w equals mg. Since g equals 9.80 meters per second square on Earth, the weight of a 1.0 kilogram object on Earth is 9.8 Newton. As we see, W equals mg. 1.0 kilogram times 9.80 meters per second square equals 9.8 newtons. When the net external force on an object is its weight, we say that it is in free fall. That is, the only force acting on the object is the force of gravity. In the real world, when objects fall downward toward Earth, they are never truly in free fall because there is always some upward force from the air acting on the object. The acceleration due to gravity g varies slightly over the surface of Earth so that the weight of an object depends on location and is not an intrinsic property of the object. Weight varies dramatically if one leaves Earth's surface. On the Moon, for example, the acceleration due to gravity is only 1.67 meters per second square. A 2.5 kilogram mass thus weighs 25 Newton on Earth and only about 4 Newton on the Moon. It is important to be aware that weight and mass are very different physical quantities, although they are closely related. Mass is the quantity of matter, how much stuff, and does not vary in classical physics, whereas weight is the gravitational force, and does vary depending on gravity. It is tempting to equate the two since most of our examples take place on Earth, where the weight of an object only varies a little with the location of the object. Furthermore, the terms mass and weight are used interchangeably in everyday language. For example, our medical records often show our weight in kilograms, but never in the correct units of newtons. Mass and weight are often used interchangeably in everyday language. However, in science, these terms are distinctly different from one another. Mass is a measure of how much matter is in an object. The typical measure of mass is the kilogram. Weight, on the other hand, is a measure of the force of gravity acting on an object. Weight is equal to the mass of an object multiplied by the acceleration due to gravity. Assuming the mass of an object is kept intact, it will remain the same, regardless of its location. However, because weight depends on the acceleration due to gravity, the weight of an object can change when the object enters a region with stronger or weaker gravity. For example, the acceleration due to gravity on the Moon is 1.67 meters per second square, which is much less than the acceleration due to gravity on Earth, 9.80 meters per second square. If you measured your weight on Earth and then measured your weight on the Moon, you would find that you weigh much less, even though you do not look any skinnier. This is because the force of gravity is weaker on the Moon. When people say that they are losing weight, they mean that they are losing mass, which in turn causes them to weigh less. Here is a sample word problem about the law of acceleration. What acceleration can a person produce when pushing a lawnmower? Suppose that the net external force, push minus friction, exerted on a lawnmower is 51 N parallel to the ground. The mass of the mower is 24 kilograms. What is its acceleration? Here is the strategy. Since net force and mass are given, the acceleration can be calculated directly from Newton's second law as stated in F net ma. Here are the given: the net force is 51 Newton and mass is 24 kilograms. For the solution, the magnitude of the acceleration is acceleration equals net force over mass. Entering known values gives acceleration equals 51 newtons over 24 kilograms. Substituting the units kilogram times meter per second square for newton yields, acceleration equals 51 kilogram times meter per second square over 24 kilograms. Cancelled same units in numerator and denominator, which are kilograms. The final answer is that the acceleration can a person produce when pushing a lawnmower is 2.1 meters per second square. Let us check your understanding of the lesson. Your task is to choose the letter of the correct answer. Type your answer in the comments section. I will give you 10 seconds to answer each item. Number 1. What do you call the rate at which an object's velocity changes over some time? A. Acceleration. B. Free fall. C. Friction. If your answer is acceleration, then you are correct. Number 2. What is a force past each other of objects that are touching? Examples include rough surfaces and air resistance. A. Acceleration. B. Friction. C. Weight. If your answer is friction, great job. And number 3. What do you call the vector sum of all external forces acting on an object or system, causes a mass to accelerate? A. Acceleration. B. Friction. C. Net external force. If your answer is net external force. Very good, you are awesome. For your assignment, answer the following word problem. Here is the summary of the lesson. Acceleration, A, is defined as a change in velocity, meaning a change in its magnitude or direction, or both. An external force is one acting on a system from outside the system, as opposed to internal forces, which act between components within the system. Newton's second law of motion states that the acceleration of a system is directly proportional to and in the same direction as the net external force acting on the system, and inversely proportional to its mass. In equation form, Newton's second law of motion is acceleration equals net force over mass. This is often written in the more familiar form, net force equals mass times acceleration. The weight, W, of an object is defined as the force of gravity acting on an object of mass. The object experiences an acceleration due to gravity. G is weight equals to the product of mass and acceleration due to gravity. If the only force acting on an object is due to gravity, the object is in free fall. And friction is a force that opposes the motion past each other of objects that are touching. If you have some questions, just type them in the comments section, and I will answer them as much as I can. Thank you so much. See you in the next lesson. If you like this video, just click the like, subscribe button, and notification bell for more videos. Thank you and God bless.